So I'm eventually in a position to talk about a full capsule net built in Excel. It's been a while trying to get the backpropagation working. That's the process by which it learns. And I think if you're looking at this blog, you must be vaguely interested in it. And you'll know that capsule net is a huge leap in the way neural networks work. And it has this really interesting idea of entities and components within the network that build up to higher levels, and the pose or orientation of these leads to a guess of what high-level networks, high-level capsules look like. In this case, it's MNIST. It's the handwritten digits from Jan LeCun, and there's 60,000 of these and a 10,000 test set, and they're all individual. And you can see that the humans tried to write a 9 here, and it's pretty sloppy. This is what was actually written in the test data set, and it's been digitized and put into a 28 by 28 frame, 28 by 28 pixels. That's 748 pixels. This is a reconstruction that's come from a decoder based on the output capsules, the output digit capsules, which in this model I've built are 8 dimensions wide. And this pretty curve here has taken 14 days to make in Excel. And it's basically 7 epochs, and I'm still training. And I'm getting up to about 98.5, which is slightly higher than the kind of 98.4, which is was the state of the art for convolutional neural network without dropout or drop connect. So you're getting about 1.6% errors. I've subsequently got a bit higher, but that tends to be because of a random starting seed, etc. So this has been trained. I'm not going to go with this one because I want some of these slowed. So I'm going to not save that one. It's running on one of the many computers on my desk. I'm going to look at this one. This one's testing at 98.7. So that's the full test set, full 10,000 digits. You can see it plowing through that with the orange line being the cumulative test rate. These are instantaneous over a period of 100, I think. So it's the average of 100% in many cases. Interesting things about this is these reconstructions, you can twiddle them, and they're based on 8 dimensions. So if, for instance, I take the first dimension over which this digit is the first dimension of the pose of the digit 8. Which is not refreshing, so I'm going to flip back to it. The first dimension, and we stretch that first dimension. Let's try the second dimension. What's happened is the capsule net has learnt effectively the linear manifold of all possible poses of the way a human writes an 8. And they found these various dimensions that allow it to encode the variation between all 8s written in the data set. Now, I've stretched these dimensions a bit too far, so I've taken one of the dimensions and I'm tweaking it while I hold all others constant. Better is probably the write-up on my blog, where you'll see this on richardmadison.com. I think it's the first blog now. What I've done is I've got 6 of these digits, and I'm stretching the dimensions 1, 2, 3, 4, 5, 6, 7, 8 for a 0, for a 1, for a 2, for a 6, for a 3, and a 4. And that gives you an indication of what the linear manifold, all possible pose orientations, looks like, because we're moving along one dimension and seeing how it varies. Now, I'm going a little bit too far, way outside 2 standard deviations that you see in the handwriting, but it gives you an idea that we've got a really thorough view of how this high-level digit varies. So back on the model, usual kind of layout you've probably seen on the other neural networks I've set up. I've got a learning curve, precision, I've got loss curve here, confusion matrix, and in this case I've got this new feature of being able to mess with the dimensions of the reconstructed capsule. Now, I think the thing that's interesting about this, and the reason I wanted to do it, was I wanted to do it on sheet. And doing this on sheet is useful because it kind of demystifies the whole thing. So I'll come back to the start of my capsule. I'll show you what it looks like. And what this is showing us, if I can unpack it and actually close this down just to the forward capsule network, this is showing you a tool in Excel that can recognize handwritten digits up to close to the human level of the ability to recognize digits. I think that's about 99.5. I can get this up to 98.7, but because it's a little bit small, and I'll explain why that smallness sort of causes the problem. But I'll talk you through the layout of the model. You're looking at the actual OnSheet model here. And it's a little bit scruffy, so I'm going to turn over to a selection of PowerPoint slides, which might give us a clearer view. Yeah. So here we've got the forward capsule network, and it breaks down into the input digit, 3, 28 by 28, the first layer of convolution, and this is a standard convolutional neural network right up to this point. And I've written a lot about those, and I've built quite a few in Excel. So again, it's demystifying these big algorithms that are driving everything in today's modern AI. This is a debatable point and would cause annoyance with a lot of people. But in 2012, when ImageNet was won by, I think, the AlexNet, suddenly, wow, convolutional neural networks came of age, and they've dominated everything since then. So they've taken over image recognition, speech translation, categorization of images, all sorts of things. And they've been being optimized for 20 years, but the Capsule Net was only released in 2007 by Hinton. So you wonder what's going to happen in the next 10 years as we optimize it. And if you've got various people playing with it, including amateurs like me doing it in Excel, we're going to find some interesting things. And arguably I have in this construction, and I've talked about it on the blog, a different way of doing the loss, a different way of doing the checking. Probably wrong, but different. So talking through the layers, we have 2 layers of convolutional neural network. The blue bits are the kernels. That's where it stores the parameters which capture all of this information. So this is the data store, or if you like, the brain. And then here we've got this huge set of affine transforms that take the capsules, where we've gone from 1D scalars that you have in a convolutional neural network. Is a feature present in a particular visual field, and that's all that scalar indicates, a probability of it being there. And in actual fact, with certain activation functions like a sigmoid, it really is a probability of 0 to 100. But with a relu, it's still an indication of the probability, but it's not 0 to 100. We squash these into 8D capsules, and then we give it a group squash. So that means we apply a non-linearity to all 8 dimensions at one time, and that ties it together into a capsule. We test it by running it through this affine transform. We do 10 of them, because we don't know which of these lower level capsules is associated with the digits 0 to 10. And that twist results in 10 guesses. Those 10 guesses of 100 primary capsules allow us to do the routing by agreement. Now, originally, I'd set this up with 3 levels of routing by agreement, which does make sense if you're doing the more complex overlapping digits that I'm coming to next. But to mimic the code that I was effectively basing this on, which was from Aurélien Geron, who did some brilliant work almost a month after Jeff Hinton had released the paper, and he did it in Keras. But trying to translate that and put it into Excel was a bit of a struggle. But this routing by agreement is effectively 1 step or 1.5 step, because we sum up these and then we squash them again to get to get an approximation of the orientation of the digit vectors, and then we use this approximate orientation and we multiply it or dot product cosine difference against all of the input primary capsules, and that prunes away those that don't follow the orientation of the digit capsule. So we get to the final digit capsule and we get a very good match, and we say, hey, this is a 0 or this is a 1. This large section to the back here is a decoder, which takes the 8-dimensional digit vector and it tries to turn it back into a reconstruction that looks like that. A few more slides. Well, if you expand this out, that affine transforms looks like this, and that's the full model with the backpropagation and the optimization of backpropagation. I used Adam, which was again was a straight copy of what people would tend to use, and also what Aurélien used. The reason I went back to one stage of routing by agreement is probably the same reason that Aurélien Geron did, which was the one of the fastest papers out by this guy, whose GitHub is Naturomics. And he actually, you're seeing that the test accuracy is higher with only one set of routing by agreement. But we do get better results when we've got overlapping digits on more than 2. Here's some examples of trying to train it up on the test set only. Now, let me explain what happened there. Lots of failures, lots of learning curve failures. The way I got this to work in the end, and I'll come back to the Excel, not the blog, I'll come back to the actual Excel, which is actually misplaced almost. Capsule Network 01, let's try this. Yeah, here it is. It was to, instead of using the full 60,000 digit training set, I based my model on the 10,000 test set, because that allowed me, with the size of the model I have, which is considerably smaller than Aurélien Geron's, to actually overfit to 100% accuracy. So I took Aurélien's code and I modified it down from the original size, which is 9 by 9 kernels, 256 channels, 16 by 10 outputs, 16 dimensions, 10 output digits, and then a massive decoder. That's 44 million parameters in his Keras model, which is a direct copy of Jeff Hinton's. And I pared this down until I got something which was only 127,000 parameters. It's much smaller, 5 by 5 kernels, mainly because I already had that built. 4 channels, 8 channels, and then 8-dimensional primary caps and 8-dimensional digit caps. Oh, I wish I had picked a different dimension for the digit capsules, because it's quite hard to understand the dimensions if they're the same before and after the affine transforms. But nevertheless, it's 8 by 8, or it's 8 dimensions on both sides. And I was getting pretty good results. I was actually getting 98.8 ultimately. I think this was one particular seed. So with a better seed, I got the right one. So that's how I chose to reduce my model down to just a test set for the build. And then I built the forward network, which took a while. And I placed in it parameters that I'd trained from Aurélien's code. Now, Aurélien's code is great. It's on GitHub. If I can find, there it is. If I can find the code, here's Aurélien's original code. It's fantastic. Look at it. He did a really good job, and he's got a couple of videos, one on the general principles of Capsule Networks, and then one on how he built it. And that really helped me, and this was the original code. Then I goofed around with it in order to get a much smaller set of numbers and to try some of the tweaks and changes that I needed. Like, I couldn't get the margin loss initially, so I just had categorical cross-entropy. And then when I eventually got that, I got it wrong. And now I think I've got something interesting that I'm going to tell you about called a brim loss, where you actually optimize for uncertainty. And for a tiny little network like mine, it learned quicker. And I think that's interesting because it's kind of closer to the brain, etc., all that sort of stuff. Clearly, the biggest influence is the guy that invented these things, Jeff Hinton. And I spent some time looking at his work, and I thought that was really interesting. So I got a lot from Jeff Hinton's paper and these things. And again, I've mentioned that in the blog, so have a look at the blog. What we're looking at here is, I think I just mentioned this earlier, so I'll skip past it, but 6 digits. It's written about in the blog, and this is the way the neural network has encoded each of these digits, and it is how it manages to so accurately identify what a human wrote when they wrote a 1 or a 0 or a 6. So Capsule Net, input image, first channel. Again, I think I've shown this a few times. We're basically sweeping that kernel across the image. So if I take a chunk of those and I show you audit from all of them, you see you cover the whole of the input image. Next, we apply nonlinearity, which is this ReLU, rectified linear units. Super simple. Only appeared about 4 years ago, and I think it's another Jeff Hinton after he'd talked to a guy who understood how the brain worked. Although he's pretty good. I think he's a neuroscientist too. And they came up with the ReLU as a much better way of doing it. This is channel layer 2, and it's you see it's taking a view on all of the 4 channels prior to it, and it's multiplying this by the four kernels for each of the 8 channels, but you don't really think about it like that. You just think about it as a 3D channel. Uh-oh, I've pressed a button which has done even more auditing. So I'm hopefully going to get out of that fairly soon. I'll flip off Excel till it calms down and go down back to the PowerPoint. So some things on the PowerPoint that I think are interesting is I've done some nice layouts. This is a description of what's happening in the forward network, and I wanted to show the big change in Capsule Nets, which is where we move from scalar identifiers of features to BAM, dimensional capsules, vectorized versions of a neural network. So basically, we just take the activation outputs for the 8 channels on layer 2, we line them up into 8D vectors, and then we apply a group squash, so they all get the same non-linearity applied to them. And that's here it is. Here's the code for a squash. It's talked about in Jeff Hinton's paper, and the idea is you're squashing the whole of the vector down to a 0 to 1, something manageable, which you then pass through the affine transforms. You take your guesses, and you use those guesses with routing by agreement to come up with a vector that represents the pose of the top level digits. So there's a transition from scalar to vector here, and this is this big chunk of code that we need, the affine transforms that allow you to grab the entire linear manifold of the digits. That's all the position, pose, skew, lighting, well, linear transformations over which these digits occur, i.e. the variance over which humans write the digits. And when you've got that linear manifold, you get this, this very interesting kind of view of what it is. And through routing by agreement, you can fix onto that manifold and get some really interesting results. So good, that's finished auditing. I'll take that off, J. And move on to activation. Here we've got the arrangement of moving the output activations of layer 2 to 8D vectors, and then here we've got the squash function, which is audit that down. All that's doing. Sorry, my audit key takes a sparse view when there's too much information. So this is, it's only giving you an indication of little bits there. So that takes us through, that gives us a vector to pass through the affine transforms to give us this guess, and that is simply the primary capsule multiplied by the affine transform. This is where I wished I'd had a different dimension for these guesses of the digit caps. They're still primary capsules, but they've been put through the transform to get them in the same orientation as the output capsule. We sum them all up. Ding! So these are the dimensions summed up 1 to 10, and then we squash them, and then we take the routing by agreement. So here we've got this very interesting routing by agreement, where we're basically multiplying or getting the cosine difference between the output sum of all of the vectors and each of those guesses, those primary capsules. We take a softmax of that. We do proper routing by agreement here now, because this is what this is doing is taking a particular dimension, it's multiplying it by the, I'll take just the last digit so you see what's going on. Oh, gosh, no. I have to take the last 2 digits. So I'm going to take 9 and 10, and I'm going to take all 8 dimensions, could be 16 dimensions, it is in the paper, but I took 8, multiplying them by this expectation or routing weight, what the coupling coefficient, I think it calls it. And then you end up with V, which is the output kind of vector for the digit capsules, and we take a safe norm of it. What we've got here, we've got the prediction, which I just took the highest argmax in TensorFlow, and then this is the truth, so what we're actually being presented with, which is an 8. And then we've got the margin loss, which is really good. This is the proper margin loss with the squares outside the maxes, and the margin loss, the derivative of the margin loss. No, that's actually my twisted version of it. So that's actually a brim loss that I'm going to talk about in a bit. If I expand this out, you can see how I got my dz. This is the gradient of the loss. Now the real gradient of the loss is the derivative of the margin loss here, and you just have to differentiate the margin loss, and you get that. And if you get a max function, you use it as rooting. But I skipped the max function and optimized for uncertainty. But how do I get that single value back through the model on the backward pass? Well, I used the digit capsule vector as the carrier for that. And again, I explain a bit more about that on the blog. So that's the forward model. If I now bang it open and show you the backward model, it gets a bit bigger. So, well, this has got some quite interesting features in, which I'll talk about now, which is backpropagation through a stride. That wasn't obvious until I looked online. And if you've got a stride, basically, you've crushed a larger dimensional field down into a smaller dimensional, half the size of the stride, more or less. But to go backwards from the gradients with respect to the loss, you have to kind of spread it out and put spaces between it. So this is, if I look at where that's coming from, it's coming from here, there. You see that you're basically spreading it out so I can stride over it. And another interesting feature is, what do you stride over it to get the dz? So here's dz, jl. And I took the kernel and I just waved it over this expanded, strided dz2, the gradient of layer 2. But that doesn't work because it's sort of upside down. And so I had to twist and flip the kernel. So if I look at what I did to the kernel here, this is fascinating. And this, given I think my original ignorance of the subject, I just played. And there's a spreadsheet jockey. You can look at the dimensions of the thing, put them together until it works. And I found that what worked was flipping this very strangely. So you see that the flip I've got there is there's the kernel for layer 2. And it's basically a reversal of the bases. And you'll see how that audits out. Now, what does that mean? Cancel? Why would you do that? Well, you do it because you get connectivity, the right connectivity path on the backward pass. Okay, so what does that mean? Here we have, say, the input image. Here we have a 3x3 kernel, and here we get the output. So that output is, basically the kernel times the image. And this one here is, it's the matrix product. It's a one-by-one product of these items. That times that. Is that scale-up? But you don't do that in Python in TensorFlow. You build this massive sparse weight sharing matrix. And if you look, this is the kernel weights, and you can see them here, but spread out for each pass of the 1, 2, 3, 4 of the output. So that's layer 1, 2, 3, 4. So if you think about stretching out the input image into a 16-dimensional column vector, that's this spread out as a 16-dimensional column vector, then the output you get a 4-dimensional column vector. And basically, that's just a matrix multiplication. You can probably see it from a formula bar what's going on there. Well, that's how they do it in code. It's apparently quicker. Which means that when you want to do it on the backward pass, you just transpose this sparse weight sharing matrix. But in Excel, it's pretty ugly. In Excel, what I did was you basically make this triple axle conversion named after Axel Paulsen. Now, I think it is because user 1551 on Maths Exchange Stack called it that, said little known. But this might just be a meme that he's getting me to spread. But in any event, you do this bizarre transpose of the thing, and then you sweep this transposed kernel over a padded version of that doesn't help, does it? Over a padded version of the input, and you end up with exactly what we want, which is the same connectivity, and that's how you do a backward pass. So if you're backward passing from this 4x4, the smaller version, to the bigger version, you can use the Axel Paulsen triple axle matrix. I've written about that on the blog if you want more detail. So back on the model, see, even this is not quite enough because this is going to train with gradient descent, stochastic gradient descent. Now, without a GPU in your Python code, if you train Aurelian's model um, with a CPU, with a normal CPU, it takes about 3 hours. It takes 5 minutes on a GPU, but 3 hours on that. And that's the big version. If you train my smaller version, it still takes 20 minutes. But if you do this in Excel, it takes ages. And that very first image I showed you of the trained model, I said it had taken 10 days. So it's just a vast amount of time to train this. And that's with Adam. Now, Adam is a mixture of momentum, which kind of corrects the orientation of the gradient as it descends to the minimum of the loss function, plus RMS prop, which boosts the speed of that descent. So this is without that. But if I pop open what I had to do to get this to settle in reasonable time, that is 10 days for 5 epochs, if I pop that out, then you get to see the enormity of the project. And it's 7,000 columns long and 1,000 columns deep. Here's the affine transforms. This is the decoder. It's blown huge. So that's how big I needed to make it to get it to run and to get it to learn up to the levels that you've seen. So I'll come off that. And how did I eventually prove to myself that I'd got it working? Well, I loaded Keras, and I got 100% overfit when I was using the test set. So basically, I loaded 100% overfit data. So I had trained it on the 10K test digits. I'd trained it in 38 epochs or so to get a 100% overfit. No, this is not these are not the Keras results for the overfit. This is actually playing with the loss. But you see here that it kicks off with 100% precision. And then I started learning. So I had 100% accurate overfit numbers on the test set, and then I started to learn. And I changed the carrier I used for the back propagation, the gradient of the loss function. And eventually found that, with a small enough learning rate, 0.0005 learning rate in 4 epochs, I was actually learning exactly the same way as the Keras code, the modified Aurelian Keras code. So hey, exciting! I got the thing to work. So now I then load up the full training set, and I load in pre-trained data, and this is pre-training the Keras code for 50 epochs. Takes a couple of hours, and I was able to get, I think, a maximum of about 98. This is a validation set, so I think I was getting 98.8. But the best one I loaded out was 98.7, and this is what you see here, 98.7. So that's learnt on the Keras code. Then I set it off learning with the new approach, now knowing that the learning actually worked, and I'm able to get close to this. So I think if I give it another week, I will achieve these results. There's lots of room for optimization in the Excel, and there's lots of room for optimization in the actual structure of it. One thing that I thought was interesting in this approach was that I made various mistakes on the loss function, and that the margin loss here's an example of it. So you set these margins, which is what Jeff Hinton's trying to do is to ignore accuracy above 0.9, 90%, and you can't really see what's going on. So let me change that threshold for the margin to 0.7. So basically, this would be the loss function that gets passed back, the gradient, but he kills it after the top end of the threshold because they're not particularly interested. Particularly, that makes sense with multiple overlapping digits. But I didn't. I kind of misunderstood the max function, and I actually penalized anything above the positive threshold, or in the case of a negative, I penalized over certainty. So if you were 100% certain that it is not a 2, or let's make it more intuitive, if you're 100% certain that this is not a 5 or whatever, you actually penalize it back to optimize for 80% or obviously 90%, 0.9. That was a mistake, but I got it to learn quicker, and I couldn't quite understand why. So it was getting up to 100% overfit much faster. So I stuck with it. I built a version with the marginals, but really with a spreadsheet and 10 days to train. I felt it might be more useful to look for something that gives speed or not. Why did I call this a brim loss? Well, I'm sure somebody else has done it. It's not particularly clever. Somebody must have done it, but instead of looking like a hat, it's got a brim on it. I'll call it whatever it really is. But it certainly worked quite well with an Excel version of the spreadsheet. I think that's kind of more or less all I've got to say on this. I'm going to put the actual spreadsheet up on my blog site as soon as my son teaches me how to put a counter, because I'd like to see if anybody downloads it. So I will be releasing the code, but at the moment, hopefully you've seen a fair bit on the screen as I talk through this code. And that will give you a chance to build it yourself if you want. Or modify the code that I'm going to put up. I'll be doing some other stuff on straight convolutional nets that I think I've pretty much mastered by now, but I don't have those. So, all comments welcome. I greatly enjoyed doing this. I'm now reasonably good in Python, Keras, TensorFlow, so I'm actually getting some interesting projects and looking for more. So if you have areas where you think this might be useful, basically neural networks, which is useful absolutely everywhere. But if you think in particular in terms of capsule nets, I've got a pretty good intuitive understanding, having made most mistakes that are possible to make over the last few months. Anyway, thank you very much for looking at this. I am delighted to have been of any interest to you.